Hello, everyone. So as many of you've heard, I actually no longer an employee at Oregon State University, so I'm sort of cheating a little bit right now. So I have since moved to Stanford University, but I'm still going to be able to talk about sort of a project that's just gearing up. And it's a little bit different than the previous presentations, that this is just all future work rather than any existing work that I'm going to be talking about today. And I just want to highlight that Gustavo, the student working on this project, is really the main person. Anything I say, you can hold him accountable. And there's also quite a few other students who I'm not listing here that are in adjacent projects that are also contributing to this work. So the title of this is Collating Experimental Data to Support the Numerical Modeling of Mass Timber Systems. So it's quite a mouthful. But I think we all, and I hadn't realized this was going to be so small, so most of the font's going to be a little bit difficult to read, but we need to think about reducing our reliance on experimental testing. And to do that, we're going to need to develop more robust numerical models. And the reason we want this reduced reliance is because physical experiments are very expensive. They're only giving you discrete data points. And so maybe numerical modeling can fill in some of those gaps. And at the end of the day, when we approach design, we need numerical models. And so we're seeing more and more guidance come out that's very exciting about how to design mass timber systems. But at the end of the day, most of these mass timber systems are still being designed according to alternative methods, which means you're perhaps using some sort of performance-based design methodology, which means that your design is as good as the numerical model you're using to design those systems. There's also this other point that if we want to codify some of these mass timber systems for seismic areas, we do need to justify our seismic design parameters, which means we also need reliable numerical models in order to get some of these systems into code, and so they can be more greatly used. And so if we're looking at design, we need numerical models, and those numerical models need to be grounded in the experimental data. So that's where I get to kind of tie in the experimental component with the numerical component. So when we look at experiments and we need that experimental data to make sure our numerical models are robust, we're looking at a whole bunch of experiments that are fragmented across different testing sites, different PIs, internationally. And so that experimental data is not all collated for us to be used, so we can actually develop and validate these numerical models in a more reliable way. And so I think every presentation before me has shown experiments. And so having that data easily and readily available will make this numerical modeling more approachable. So we have this test data at the material level, and then we have these more system level test data that's also going to start becoming available. And so when I look at this, up until this point, we've really been saying, well, we don't really know how mass timber behaves. We don't know how the energy dissipators can be connected into them, but we're starting to get quite a bit of collection of data that we can now use to validate our numerical models. And so I would argue that we're at the point when we can start thinking about how do we use this available test data to support numerical models and ultimately design. And so that was the ultimate crux of this work, is to gather that existing experimental data, put it into a mass timber experimental database that's readily available to the community. And then finally, sort of use that to benchmark a few key models that could also be available as examples for how we might numerically model these systems. So you've seen this trio before. They're also on this team as well. So my co-PIs, Ari and Andre, and then of course the student who's really doing most of the work, Gustavo. And so we're sort of basing this initial database on these sort of system level tests that we're doing with the 3-story and the 6-story system, as well as the many experiments that Ari and Andre have conducted in the past that are available at Oregon State. And so our first step is to develop some sort of data hierarchy. So we can look at the material level, we can look at the component level and connection level, and finally, as the system as a whole. And again, this initial data collection is really going to be sort of an Oregon State driven effort, but we're hoping that any future additions to it will be community driven. And so if you have done an experimental test and you want that data to be available, you would put it into this searchable open database of this experimental data. And ultimately, once that we're hoping that database will then lead to greater modeling guidance for these mass timber systems. And so far, we've just initially started the data collection process. And so we have about 32 tests, and we're sort of thinking about what sort of metadata goes into each of these experiments. So an ID, a reference, specimen name, data type. And then again, we're hoping that any future experiments will then be added to this, so this can ultimately be used by the mass timber community. So then that follows on to the actual numerical modeling part itself. And so we can start beginning to think about sort of benchmark numerical models that can be used in design. And so right now, the initial focus is just on the 3-story and the 6-story tests, because I'm also on those projects, Gustavo is also in that project, and those test data is readily available and we know what it looks like. And so we've been focusing on these 3-story and 6-story tests that you've heard a lot about so far. The 3-story tests, again, hopefully all of you will get to see it, is at the Emerson Wood Products Laboratory. And, you know, I wish I would have talked to my co-PIs, or else we wouldn't have the same figures in all of these slides. So all of you are now familiar with this 3-story mass timber gravity system, which allows us to swap out the lateral system and test a few different mass timber design solutions. So the idea of this mass timber spine is that you have some sort of elastic component running over the height of the structure. And so it could be either rocking and uplifting like you see here, or it could sort of pivot about a pinned base like you see here. And I'm just noting the different components that we need to then think about when it comes to our numerical modeling. So each one of these features needs to be noted on whether it's critical or not critical to the design and analysis of a mass timber system. And then each of those components that we decide are critical then need to be validated with the experimental data. So this is really, you need to capture all of the relevant components. So just focusing on the pivoting spine that's in the 3-story system right now with the BRB sort of boundary elements. So you have the MPP wall itself, you have the energy dissipators, in this case, the buckling restraint brace, then there's the pin at the base of the system, as well as the gravity system and diaphragm that lateral system is connecting into. And each of those different components, we might have a couple component test data that we can pull from, and then we want to then validate the entire system as a whole. And so this is just what it looks like in reality from the experiment. And so just starting to look at the different aspects of these tests that we would then need to model. Well, we could sort of approach it at first just from looking at the lateral system itself in a very simplified way. So in this case, we have this pivoting wall like you would see here. And so we have a relatively simple model that represents just the lateral system. So this could be square one, and it's going to allow us to sort of identify those modeling practices that we can use for design and assessment, just focusing on the wall. So we can look at just the behavior as a whole. So we expect that we'll update these models after the experimental test. But then when we look at these experiments, there's a lot of other different components going on. So, you know, here's an actual mock-up of the lateral system sandwiched in between the gravity system. And when we look at the numerical model, and starting to explore the other modeling features that might also be relevant, we get something that's a little bit more refined, and we get a little bit more detail in our numerical model. And so we're looking at this numerical modeling approach from the simple, as well as the most refined, and then selecting the modeling features that are most relevant to all of you. Some things to think about. There are details here that we need to think about how to best model. So for example, we could model every inclined screw. We could come up with a continuum model for some of these connection details. We could think about maybe developing spring type models that connect the diaphragm to the walls themselves. And so there's a level of hierarchy and fidelity that needs to be thought about. At the end of the day, we want our numerical models to most appropriately represent the physical experiments that we're attempting to emulate. So this is sort of step one in this grand scheme of numerical modeling that hopefully I'm trying to give to all of you. So for example, numerical modeling of the buckling restraint braces. Here we have a BRB where we can validate some of the components individually before placing it into our full system model. So we want to then represent this BRB with something that's maybe a combination of co-rotational truss elements, so some sort of line elements representing the BRB and connection regions. And so what we did is that we then went to the experimental data that was available for BRBs, and we said, well, we want to minimize the mismatch between the experimental data and our numerical modeling outputs. And so you can imagine something very similar to this. This is in terms of the mismatch between forces, but it could be mismatch between stiffness, energy dissipation. This is sort of the beginning look at some of these models that we're building based on the test data. But you can imagine having a number of different experimental data points that you can then minimize the mismatch between your experimental and numerical models. And so this is just an example for the BRB test data. This is still a work in progress. And so we have the experimental data in gray, and then the blue is the output from our numerical model. And just something to note is when you put buckling restrained braces into these sort of mass timber systems, there's not actually a lot of BRB data out there that's suitable for this sort of hybridization of BRBs with mass timber. And that's because most of the BRBs you're using tend to be pretty small in order to connect into the wood. So you want to be able to develop the strength of the BRB. And so you tend to look at smaller BRB sizes that are what are typically used in the steel industry. And so this one on the left is probably the most similar on what we're using in the 3-story test. But then we wanted to look at sort of varied loading protocols, the effect of larger deformations. And so combined, this gives us really only 3 tests, which we're then looking at in terms of our numerical model. And so collating all of this experimental data in one place so that we can then get sort of a greater, what's the word I'm looking for? Better numerical models that best represent the experimental data that we have is critical. And so this work isn't by itself, it's actually nested on the several projects that you've heard about earlier today. So this is a 3-story Emerson project, the 6-story shake table test that will, the 10-story that will then turn into a 6-story shake table test at UC San Diego. And then this one sort of wrapping around both those in the development of these numerical modeling methods that will hopefully support better guidance on modeling and design procedures for these mass timber systems. And I just want to end with this last slide, and I'm glad that Andre didn't show it. So, and this is thanks to Stephen for making this slide, because I think it's probably one of the best ways to start thinking about how we can start approaching sort of design in the mass timber industry. And so we're lucky in that as we think about mass timber design in seismic regions, we want to be able to support this idea of resiliency, of being able to bounce back after a significant seismic event. We also have sustainability benefits that are coming with these types of systems. And then hopefully the combination of those two things and the fact that mass timber has not quite been codified yet will also foster innovation in this industry. And so as we're thinking about how to design for these types of systems, we get to consider both resiliency and sustainability metrics and sort of start thinking about our design in a new way. And as we're sort of supporting these new design methods, that's where numerical modeling really becomes the key piece. And so, I realize a lot of this is mostly future work, but we're hoping that with collating this experimental data in a database, building some benchmark numerical models, we can then support these 3 items on the bottom. And so I'll just end there, and then hopefully I talked fast enough where there's no questions or.